We're going to explore linear programming. Linear programming is a method that we use to find the best solution when there are linear equations and or inequalities involved. So here we have some linear inequalities. So here's our linear inequalities. Let's get that pen working there. We've got linear inequalities, and then what we also have is an objective function. So here's our linear inequalities right here. That's these right here. We also call those constraints. And then we have an objective function. So I'm going to refer to the objective function. So you'll want to know what that is. And then these inequalities are called constraints. Constraints. So they're constraints on a particular problem. So usually you might see something like this in a manufacturing situation where they're trying to plan on how much labor they can afford compared to how much they need to manufacture for consumer demand. So what we want to do is we want to optimize. That's another word. This is optimization. We want to optimize an objective. Optimization. So that's usually maximizing or minimizing. Maximize or minimize. Either one. It all depends on whether or not you want to maximize your profits or minimize your cost. So what we're going to do is we're going to write down our steps that we're going to take. The first thing that you want to do when you have or when you're faced with this linear programming situation is you want to graph your constraints. So graph each constraint on the same grid. You want to define the feasible region. So identify or define, identify the feasible region. And then that feasible region is going to be an enclosed, hopefully it will be an enclosed region in which we'll have vertices. So we'll want to locate those vertices. So locate the exact vertices. Now exact is an important part of this. Locate the exact vertices of that region. And then our last step will test each vertex for either a maximum or minimum of the objective function. So that's where the objective function will come into play. So we're going to graph x is greater than or equal to 0 first. X is greater than or equal to 0. Well, that's a vertical. It's a vertical line. So there's x equals 0. And I'm going to write on it x equals 0. And x is greater than or equal to 0 when we shade to the right. So I'm just going to draw arrows that shade in that direction. Our next inequality is y is greater than or equal to 0. So that's a horizontal line on the x-axis. And I'm going to label that y equals 0. That's the boundary line. And y is greater than or equal to 0 above that line. And then we have 2x plus 3y is less than or equal to 12. 2x plus 3y is less than or equal to 12. This is easiest for me to do using my x and y intercepts. So I've got x-intercept at 6. I'm going to do this one in red. So this one is going to be in red. My x-intercept is 6, 2, 4, 6, right there. My y-intercept is 4, 2, 4. And I'm going to connect those dots. There we go. And I'm not really concerned with what's happening outside of quadrant 1 because I can see that I'm restricted to quadrant 1 just by the arrows for x equals 0, y equals 0. For those boundary lines, my inequalities are keeping me into quadrant 1. Now we need 2x plus 3y is less than or equal to 12. So if I put a 0 in for x and y, I'd be looking at this point right here. Is 0, 0 going to make that inequality true? And it does. So we will shade below. So right now I'm in this triangular region right here. Okay, our next is x plus y is greater than 2. X plus y is greater than or equal to 2. So I've got x and y intercepts at 2. And greater than 2, if I were to put 0 in for both x and y, the origin, 0 plus 0 is not greater than or equal to 2. Therefore, I'm shading away from the origin. And then my last is 3x plus 2y is less than or equal to 12. Well, that's going to give me a 2, 3, 4, an x-intercept of 4 and a y-intercept of 6. We'll connect that right there. Now, I put this in color. If I wasn't using color, I would definitely be identifying my lines using the equations. So this green line would be labeled 3x plus 2y is equal to 12. I'm going to put equal to 12 only because that's the boundary line. Now, the inequality is less than or equal to 12. That's going to keep me shaded this way. So I can see that I have this region right here that is the feasible region. So here are my vertices. I've got 5 of them. 5 vertices. Now the red and the green, 3x plus 2y equals 12, and the red equation is 2x plus 3y equals 12. 2x plus 3y equals 12. I need to figure out where that point is. It looks like that point might be 2, 3, but I need to check for sure to make sure that that's accurate. So I need to solve that system. So I'm going to take 3x plus 2y equals 12. I'm going to take 2x plus 3y equals 12. I'm going to multiply the first equation by -2 and the second equation by 3. So we get the green equation becomes -6x minus 4y equals -48. And -24. I can multiply -24. And then the red equation becomes 6x plus 9y equals 36. That gives me 5y equals, looks like a positive 12. So y is equal to 12 over 5. So that ordered pair is not right 2 up 3. So this is a great example of why it's so important to solve that system. We're going to take the 12/5, we're going to plug it back into either one of the equations. You can plug it into the green one or the red one, it doesn't really matter. When you do that, 3x plus 2 times 12/5 equals 12. You solve that, 3x plus 24/5 equals 12. However you want to solve that, we're going to end up getting x equals 12/5. I encourage you to take the time to make sure you know how to do that with fractions Very important skill for you to have at this level. So our ordered pairs for our vertices, are, let's see, we've got this one right here. I'll start here and then I'm going to go clockwise. So I've got 2, 0. The next one is 0, 2. It doesn't really matter where you start. The next one is 0, 4. The next one is 12/5, 12/5. And the last one is 4, 0. So 5 vertices. So let's quickly go back and see what we've done so far. We've graphed each constraint. We've identified the feasible region. That's what we shaded in yellow. That's important for you to shade that. Locate the exact vertices of the region. We've done that. And now we need to test each vertex for the maximum of the objective function. So that objective function is z equals 3x plus 5y. So we're going to take our first ordered pair, z equals 3 times 2 plus 5 times 0, and that gives us 6. So we're going to do that for each one of these ordered pairs. I'm going to make a little bit more room here. Spreading them out just a little bit. You're probably getting a head start on me on doing these other calculations. Z equals 3 times 0 plus 5 times 2, which is 10. Z equals 3 times 0 plus 5 times 4, which is 20. Z equals 3 times 12/5 plus 5 times 12/5. So we've got 36 plus 60 is 96 fifths. 96 fifths. It's not going to be larger than 20. It's going to be 1 and then 46. That's going to be 19 and 1/5. And then our last one, z equals 3 times 4 plus 5 times 0, which is 12. So we want to maximize or minimize. What did it say there? Maximize or minimize? We wanted to maximize. So we want to maximize this objective function. So which vertice gives us a maximum value for z? And that would be this vertex right here, 0, 4. That gives us a maximum value. So we want to maximize it. So our answer is, here's our answer. Our answer is 0, 4 maximizes the objective function. And it maximizes the objective function while meeting the constraint limits. What is the maximum value? The maximum value equals 20. So we're going to try another one of these in the next video. Make sure that we've got it, and then we'll have a couple to try. Actually, I think in the next one we'll have you try the maximum, and then we'll do an example of a minimum, and then have you try a minimum.